Morning, guys. You doing okay? Listen, today we're just going to do the clicker questions from this last chapter. And then if you have questions, we can go over stuff. If you just want to review other things, that's fine. We can do that. But I'd intended just that we would do the clicker questions for chapter 10, which I don't think that we've done except for the ones in the text in the workbook. All right, so let's go through. Oh, and by the way, so I posted your class participation points. If you get 50 points, that's the maximum that you get. Yeah. Although you can't lose points. So if you have 50, it doesn't matter if you place it or not, because you're maxed out at that. All right. All right. So which is the largest unit? 1 Celsius degree, 1 Kelvin, or 1 Fahrenheit degree? Remember, we talked about this, but it has to do with how we set up our scales. Which one is larger, Celsius, Kelvin, or Fahrenheit degree? Remember, our Celsius scale is set for the boiling and freezing points of water being at 100 degrees Celsius and 0 Celsius. The Fahrenheit is set for 32 and 212 for the boiling and freezing points, or freezing and boiling points of water. And then the Kelvin scale is set on something different, the triple point of water and absolute zero. Right, I'm going to stop at 118. You can see questions similar to this on the test, and the answer here is D. The Celsius degree and the Kelvin degree, they have the same size, and it's bigger than the Fahrenheit, because the Fahrenheit degree, I go from the boiling point to the freezing point. I have like 180 marks in between here, but for Celsius, I only have 100 or so. So since I have fewer increments for the Celsius scale, those degrees are bigger. It turns out that minus 40 is the same temperature as minus 40 degrees Fahrenheit. Is there a temperature at which the Kelvin and Celsius scales agree? And if so, which is it? All right, we'll stop at, say 40 seconds. Okay, D is right. Remember, those Celsius and Kelvin scales are separated by 273. If you go back on your equation sheet, you need to be familiar with what's on your equation sheet anyway, but if you go on your equation sheet, then it has those conversion factors, the way we convert between the different temperature scales, and notice the Celsius is the Kelvin minus 273. They're always offset by that. So there isn't a temperature in Celsius and in Kelvin where they're the same physical temperature. You notice that a mercury and glass thermometer is inserted into a hot liquid. The mercury column first drops, and then later starts to rise. You would expect it to rise as the temperature increases. Why do you see that drop? So when you put a thermometer into a hot glass of water or whatever, initially the temperature drops, and then it increases. How do you explain that drop? All right, we'll stop at 55. Okay, good. D is right. The glass expands before the mercury expands. Because when I put this mercury thermometer in a cup of hot water, it causes the glass to expand first, because the glass increases temperature first, it gets bigger, and that mercury just sort of falls back into that now bigger bulb at the end of our thermometer. So the correct answer then is D. The glass expands, and then later the mercury will expand, and it'll actually go up the column of the thermometer. Two drinking glasses are stuck, one inside the other. How would you get them unstuck? Think about our linear expansion, or you might just know this as you go to the kitchen, if this ever happens. How do you get them unstuck? All right, I'm going to stop at 35. Oh, come on. It's C. Who put E? You're not going to. Okay. All right, so see, you run hot water over the outer one. When you have the two glasses, one stuck inside the other, if you run hot water over this one, it causes that glass to expand, and then you can take them apart. There's another way to take them apart. How is that? It's not listed here, but there's something else that I could do. I can put cold water on which of them? The inner one, right. If I put cold water on this glass, it causes it to shrink up. Now that doesn't work quite as well. It's not as efficient as putting hot water over the outer one. I don't like this question, but it's a good question. I used to be a bartender, like when I was in college, and now I still have nightmares about, anybody wait tables or, yeah, my nightmare is that I break a glass in the ice bin. Like literally at night when I have bad dreams, that's what it is. Because that's terrible. Like if you're tending a bar or working in a restaurant, because you got to melt all the ice out, you got to make sure all the glass is out. It's a nightmare. Okay, a steel tape measure, I think we had a similar one to this, gives accurate length measurements at room temperature, and if the tape measure is used outside on a very hot day, how will its length measurements be effective? We had a very similar question, but it was sort of the reverse. Here I have one that's made for room temperature, but then I use it outside on a very hot day at a hot temperature. How does that affect the length measurements? Are they too small? Are they still accurate? Or will they be too big? Okay, I'm going to stop at 50. Okay, good. A is right. My ruler, you think about this ruler. Here it is at its regular measurements. And here's my object that I measured to be 2 units long. But if the ruler gets bigger, that means these increments are now farther apart. And now my object is here, and I just measure it to be less than 1 unit long. So my measurements are too small because the ruler is now bigger than it was before. Metals such as brass expand when heated. And so here I have this brass plate. When the plate is heated, what will happen to the hole? Will the hole get larger, get smaller? Will it stay the same, or does it vanish? Now you might not know a priori what the answer is to this, but just do the best that you think. What will happen to the hole? Will it get bigger, smaller, stay the same, or does it just go away completely? All right, we're sort of split up on what we think the answer is. I'm going to stop at 45 and I'll show you. Okay, the answer is A. It gets bigger. The hole will get bigger. I know you might think, I know what you're thinking, those of you that get smaller, that the metal expands in this direction, and then it also expands in this direction. And I know that's what you're thinking, but think about it in a different way. Think about instead that I have like a piece of metal right here,
and I have a piece of metal right here, and they go around. I have these little lengths of metal that make up this circle. What happens as those little lengths of metal get longer is that circle gets bigger and bigger. So that's just something you need to remember, that if I have a hole like this and I heat it up, the hole gets bigger. If I cool it down, the hole gets smaller. It'll become important in some of the later questions that we'll deal with, and you might actually see something like that on the test come Monday. So as I heat it up, it gets larger. Okay, that's sort of relevant here. I have a steel ring that stands on edge with a rod of some material inside. So I have this part is steel, the ring, and then I have some material, I don't know what it is. But I want it so that if I heat it up, that the rod will eventually touch the top of the ring. So I heat this system up at the same rate, and I want this to eventually touch the top of the ring. What must that material be made of, the rod? Aluminum, glass, steel, aluminum and steel, or all three? Like, could it be either aluminum or steel? All right, I'm going to stop at 58. Okay, good. I'm pretty sure you're going to see a problem. I forget if I put a problem like this. I'm pretty sure that there's a similar problem to this where I ask you about the expansion rates of different materials. Okay, so here I have two materials and they both expand at a different rate. The steel, which is the ring, expands at a rate given, about 5 times 10 to the minus 4. And I want a material that will expand at a faster rate. That means I want a material that has a bigger expansion rate. And a bigger expansion rate is aluminum. Aluminum has a bigger expansion rate. That means it gets bigger at a faster rate than steel does. So aluminum then is the right answer, because the aluminum will get bigger faster than any of the other materials which have a smaller expansion rate. So listen, if I have a bigger expansion rate, my coefficient of linear expansion, if that's bigger, it gets bigger at a faster rate. It also gets smaller at a faster rate as you cool it down. That'll become important later, like right here. I want to take apart a couple of aluminum parts that are held together by steel screws. What should I do to it? So I have something that's made of aluminum, and it has a steel screw inside of it, and the steel screw is stuck or whatever, and I want it to either heat it up or cool it down so that it's easier to get out the steel screw. Which of these should you do? Should I heat it up or should I cool it down? All right, I'm going to stop at 40. These questions sometimes trip up students, but you'll see one similar to this. Stopping at 40 on Monday. Okay, so let's look at this. Our coefficients. Aluminum has a bigger coefficient than steel. So if I heat up the aluminum and the steel at the same time, the hole in the aluminum will get bigger, and the steel will get bigger too, but not as fast as the aluminum, and not as much as the aluminum. So if I heat up the whole thing, the aluminum gets bigger, the steel also gets bigger, but not as much, and I will be able to take it apart. Who answered C? Tyler, was that you? I'll find out. Like, I can find out. Okay. The grandfather clock uses a brass pendulum to keep perfect time. If it's a hot day, how does that affect the pendulum of the grandfather clock? I'll remind you the period of a pendulum. We saw this earlier, but it's 2 pi square root of L over G, where L is the length of the pendulum. All right, I'll stop at 40. I'm going to stop at 40, just a few more seconds. Okay, good. So the pendulum gets longer, right? As I heat it up, the pendulum gets longer, and that means that the period of the pendulum gets longer, so it takes longer for the pendulum to go back and forth, and that means that your clock is going to run slower. Which has more molecules, a mole of nitrogen or a mole of oxygen gas? All right, I'm going to stop at 25, 25. Okay, good. They're both the same. Remember, a mole is a mole is a mole. It doesn't matter what it is. It just tells you the number of particles, atoms, or molecules that's in that particular sample of material. You can have a mole of, I don't know, puppies or whatever, although that'd be a lot of puppies. But a mole is a mole is a mole. Which weighs more, a mole of nitrogen gas or a mole of oxygen gas? I would normally give you the atomic mass, or molecular mass in this case, but which one is heavier, nitrogen or carbon? I don't know. As in like the particular atom. Nitrogen, right? Because it's carbon, nitrogen, oxygen. So which weighs more, a mole of nitrogen gas or a mole of oxygen gas? I'll stop at 35. 35. Okay, good. A is right. Right. A is right. All right. Two identicals have the same temperature, are at the same temperature, contain the same gas or the same type of gas. If A contains 3 times as much gas as B, which has the higher pressure? Think about your ideal gas law, and as I change one variable, how does that change the other variable? In this case, I'm looking at the pressure. I want to know which has the higher pressure. All right, we'll stop at 52. 52. Let's guess if you're not sure. Good. All right, let's think about the ideal gas law. Ideal gas law is PV equals nRT. Container A contains 3 much times gas as container B. So let's ask ourselves the question of, what if we increase N? How does that affect the pressure? Well, if I increase N, like container A has more gas, so that means it has a higher N, that means that my pressure also increases. So the one with the higher pressure is the one with more gas in it, and that's going to be cylinder A. It has more gas in it. You'll see some questions like this just asking you to think about the ideal gas law and how different things affect other variables. But in this case, if I put more gas into the container, the molecules sort of interact more, they bounce off the walls more. That gives you a higher pressure in the container. All right, this one's similar. Which has the higher temperature? I think we might have had this question before. I'll stop at 28. 28. Okay, good. B is right. The one with a higher temperature is the one with less gas, and that might sort of be counterintuitive to you, but it is from the ideal gas law that if I have more gas in a container, then the temperature is going to go down. That assumes also that I keep a constant pressure. Normally, if I add more gas to a container, then my pressure also increases. But if you can keep that pressure constant, then your temperature will actually decrease. Remember, that was one of our ways to measure the temperature, is to have a constant pressure, or excuse me, a constant volume thermometer. And when the temperature changes, then that affects the pressure. Plastic soda is empty and sits out in the sun, heating the air inside. Then you cap it and put it in the fridge. What happens to the bottle as it cools? All right, I'm going to stop at 35. Okay, good. C is right. You might have done this. Have you ever done this? Yeah, maybe not, but have you done it? No. Okay, when the temperature drops, then the pressure on the inside is going to drop. PV is nRT, so if the temperature drops, P drops, and then that causes the pressure from the outside to cause it to collapse inward. What happens to the volume of a balloon if you put it in the freezer? Does it increase, not change, or does it decrease? It's a balloon that's, blown up, and then you put it in the freezer. All right, I'll stop at 25. Okay, it does decrease, just like the soda bottle. It's the same question as the soda bottle. And I think that's it. All right. I can also, if you have questions about this material, that's sort of the end of what I had intended, just that we would go through those. A few of you were sort of just missing a little bit on your class participation. But if you have questions about this material, we can address those. Feel free to leave if you want, but if you want to hang around, if you have questions, you're welcome to. All right. So, any questions right now? We're going to have a bigger review on Friday. No? Well, while you're sort of packing out, I'll tell you my other nightmare. Like I have these recurring nightmares. Like my wife, she dreams of tornadoes because she grew up in the Midwest, right? And that's what they have there. And today there is a tornado watch, by the way. But my other nightmare has to do with exam day. I guess I just sort of have this general anxious dream about giving exams that one dream I'm giving out exams and I get to the very end, there's like 3 people left and I run out of exams. And I don't have an exam. So what do you do? Are you just going to leave the class and go get more exams? Are you going to take an exam and go copy? I don't know what you do. So that's why I'm always counting to make sure I have exactly the right number of exams. And then the other thing is that all the students are coming in and they're just all talking. Like everybody's talking during the exam. And I'm really upset because all the students are talking. I don't know why they're talking. They know they're not supposed to be talking. But everybody's talking, and they're like shouting answers across the room, and I don't know what to do to stop it in the dream. So, have you done that? No.
You just fail everyone in the
I probably just failed everyone, yeah. Okay, well, y'all have a great day. If you want to hang around, we can, if you have questions, or I'll see you on Friday.